In January 1913, deep inside the Culebra Cut of the Panama Canal, the Cucaracha Slide gave way. Over 1 million cubic yards of earth collapsed, burying 5 train tracks in the bottom of the canal. Geotechnical engineers study these failures to answer a single question. At what precise mathematical threshold does an earth slope collapse under the weight of gravity and internal water? Every slope is caught in a physical tug-of-war. Gravity creates a driving force, shear stress, attempting to pull the mass downward. The soil counters with its own resisting force, shear strength, holding the mass together. Engineers calculate the outcome using the factor of safety, a ratio dividing available shear strength by applied shear stress. The resisting strength on top comes from the Mohr-Coulomb failure criterion, combining natural cohesion with internal friction between soil particles. As long as the strength outmatches the stress, the slope holds. But if that ratio drops to 1.0 or below, the forces reach limiting equilibrium. At that exact point, a slide is mathematically guaranteed. However, calculating that ratio requires knowing exactly which mathematical model to apply. Slopes fall into 2 distinct geometric categories that dictate the math: infinite and finite. Infinite slopes, like vast natural mountainsides, fail translationally, sliding downward along a straight parallel plane. Finite slopes, like constructed embankments, have restricted boundaries. They fail rotationally, carving out a deep, curved arc. Because the failure shape dictates the mechanics of the slide, classifying the geometric boundaries of the slope is the necessary first step before any stability analysis can begin. An infinite slope represents a boundary surface where the depth of the sliding arc is negligible compared to its overall length. If we isolate a single vertical block of soil within the slope, its downward weight factor splits. One part pushes directly into the slope as normal stress, while the other component pulls parallel to the surface as shear stress. To establish the foundational physics, we start with the simplest possible condition: a completely dry, cohesionless soil, like clean sand. Because the sand particles do not stick together naturally, the cohesion value is 0. With cohesion removed from the Mohr-Coulomb equation, the soil's entire capacity to resist sliding relies solely on the internal friction generated by the normal stress pressing the sand grains against each other. This simplifies the factor of safety down to a remarkably clean equation: the tangent of the internal friction angle divided by the tangent of the slope's physical incline. For the mass to remain stable, the physical inclination of the hillside can never exceed the angle of internal friction of the sand itself. For dry sand, stability is entirely independent of the depth of the soil mass or its unit weight. The only variable that matters is the friction fighting against the angle of the hill. But most natural soils are not clean sand. They contain clay and silt, adding the variable of cohesion back into the mass. Cohesion makes stability dependent on the depth of the soil mass. Because shear stress increases the deeper you go, there will eventually be a specific depth where the driving stress matches the soil's cohesive strength. We call this the critical depth. At this exact horizontal plane, the factor of safety equals exactly 1.0. The mass above this line is stable. At the line, it is on the verge of failure. By extracting the soil's cohesion, its unit weight, and this critical depth, engineers can formulate the Taylor stability number. This creates a dimensionless parameter. It represents the ratio of the soil's internal strength to the weight of the mass it must support at a specific depth. Because this number is dimensionless, engineers can plot it onto standardized charts.
This allows them to look up the maximum safe height for an embankment based on its material properties and slope angle, bypassing the need to re-derive the physics for every new construction project. That complexity peaks with finite slopes. In earth dams and highway embankments, the restricted height and base mean the earth no longer fails in a straight line. It carves downward in a rotational curve. This creates a difficult analytical problem. The failure will not occur on a single predictable plane, but rather along one of an infinite number of possible circular arcs running through the embankment. To solve this, geotechnical engineers run massive iterative tests. Using techniques like Fellenius's method, they mathematically check dozens of potential slip circles until they isolate the one critical arc with the lowest possible factor of safety. They calculate the forces acting along this curved surface by using the method of slices. This technique breaks the sliding mass of Earth down into narrow, individual vertical segments.
Because the failure plane is a curve, the physical geometry changes across the arc. The base of a slice near the top of the slope sits at a steep angle, generating high downward shear stress. But a slice near the bottom sits nearly flat, contributing primarily normal stress. By calculating the weight and angle of each slice individually and then summing those forces together, engineers can accurately compute an aggregate factor of safety for that specific curve. Analyzing rotational failure requires breaking a complex curve geometry down into linear, manageable segments. Yet even the most accurate geometry calculations can be rendered useless by the most volatile variable in geotechnical engineering, internal pore water pressure. This diagram shows a steady-state earth dam holding back a high reservoir of water. The flow net inside the cross-section represents the gradient of internal pore water pressure. Under these conditions, external water actually provides stabilizing hydrostatic pressure against the dam's face. But consider a scenario called rapid drawdown. The external reservoir water drops rapidly after a flood or an operational release. The external water is gone, but the earth and soil has very low permeability. The internal pore water remains trapped high inside the structure, unable to drain fast enough to match the dropping reservoir. At a microscopic level, this trapped water actively pushes the individual soil particles apart. This drastically reduces the normal stress, the mechanical force pressing the soil grains together. In the Moore-Coulomb equation, a massive drop in effective normal stress mathematically zeroes out the soil's frictional shear strength. The dam has lost its external hydrostatic support, precisely at the moment its internal structural strength is at its absolute weakest. Rapid drawdown turns water from a stabilizing weight into a destructive wedge, making it the ultimate stress test for any earthen structure. Guaranteeing the stability of an earth structure requires mapping these massive intersecting variables. You classify the geometry, calculate the exact ratio of cohesion and friction, and track the internal fluid dynamics. The resulting factor of safety is never a static guarantee. It is a highly dynamic ratio that fluctuates continuously in response to heavy rains, time, and human excavation. By mastering these mathematical models, engineers design physical reinforcements, like soil nailing or retaining walls, that boost the resisting strength where it is needed most. The mathematics of limiting equilibrium provide the objective threshold for these designs, turning the physical uncertainty of Earth masses into a manageable engineering limit.